Welcome back to the deep dive. We take these really complex, dense research papers, pull out the crucial bits, and basically make sure you're up to speed without needing a PhD to read them. Today, we're tackling a really important one in applied ecology. It's called optimally managing under imperfect detection, a method for plant invasions. The lead author is Tracy J. Regan. And our mission here, well, that's vital because it's all about managing invasive species. It costs a fortune, and there's this massive uncertainty. You often just don't know if the weed you're fighting is actually gone.
Exactly. And this isn't just, a small academic point. It's a huge economic problem. Invasive plants, they're a major global threat. Agriculture, natural ecosystems, you name it.
And the cost is staggering, right?
Oh, absolutely. Globally, the economic hit is estimated around, US $560 billion every single year. So if management teams are pouring money into controlling these things, digging, spraying, but they can't actually confirm if it worked because, the weed's hiding.
Then the money's just wasted.
Pretty much. We really need better tools, decision support tools that help us manage that uncertainty, not just the things we can easily see.
Okay, let's dig into that. The core challenge, imperfect detection.
Yeah.
Why is managing invasive plants so much harder than, say, counting rabbits? It's about complexity and, not trusting what you see.
Yeah, it's fundamental in ecology, really. You almost never know the true state of the system. Surveys aren't perfect. Some species are just hard to spot. They might only pop up briefly.
And the seed banks?
Ah, yes, the seed banks. That's critical. You've got this massive reservoir of potential threat buried in the soil, sometimes for years. You could walk right over an infested site, see absolutely nothing.
But it's still there.
Exactly. Your survey just failed to pick it up. The system could still be heavily infested.
Right. So to make this concrete, the paper uses a specific, quite nasty case study.
Yeah.
Branch broom rape, or Banche ramosa. It was actually targeted for national eradication down in South Australia.
And it's a real nightmare for farmers. It's an annual obligate parasite. That means it has to latch onto the roots of a host crop to survive. Think tomatoes, potatoes, canola.
And the damage is severe.
Devastating.
Yeah.
Crop losses are often reported between 75%, even up to 90%. It just sucks the life out of the host plant.
But it's not just the direct loss, is it? There's a bigger economic threat.
That's right. It's the threat to export markets. Many countries won't import produce if there's a risk it carries broom rape seeds. So for Australia, the potential long-term cost was estimated at $1.7 billion. Huge stakes.
Okay, so devastating weed, massive potential costs.
Yeah.
And detection.
Extremely difficult. The plant itself is only visible above ground for a short window. Most of its life cycle happens underground, attached to the roots.
Unseen.
Completely unseen. And worse, the seeds, they're like dust. Tiny. And they can stay viable just waiting in the soil for up to 12 years.
12 years, that's incredible, like a hidden time bomb.
Precisely. Trying to track it is like trying to track, smoke. It's invisible, microscopic, and it hangs around for over a decade.
Okay, so huge problem. Impossible to be sure what's going on underground. How on earth do you build a strategy for that? The paper starts with existing tools, right? Markov decision processes, MDPs.
Yeah, MDPs are a standard tool in decision theory. They're great for modeling systems that change over time, where you have different states, like maybe a site is infested, low density, or clear, and you want to figure out the best sequence of actions to take to maximize some benefit.
They sound powerful.
They are. They help find the optimal path forward if you know the state of the system.
Ah, there's the catch, if you know the state. But we just established you often don't, especially with broom rape. MDPs assume perfect detection.
Exactly. They assume that if the model says the site is clear, then you know for sure it's clear. And for things like broom rape seeds, that assumption just completely breaks down. You can't trust your survey data entirely.
So the paper needed something else.
Right. And this is where their novel approach comes in. The partially observable Markov decision process, the POMDP.
Partially observable. Okay, so it acknowledges you can't see everything.
Precisely. It formally builds that uncertainty, that imperfect detection, right into the decision-making framework.
And this changes how managers think, right? It's not about the actual state anymore.
Well, not directly. It's about the belief state. Instead of saying the site is empty, the POMDP works with probabilities. It asks, based on our surveys, our past actions, how likely is it that the site is actually in state A, B, or C?
So it's like, what's the chance the seed bank is still there even though we haven't seen a plant for 3 years?
Exactly that. The decision what to do next is based on that level of belief, that confidence, rather than assuming the observation is reality.
That feels like a big shift. So how did they define the states and observations for broom rape?
Okay, so the underlying real system states, S they used, were empty, say, meaning truly no seeds or plants, seeds only, SS, so just the dormant seed bank, and seeds and adult weeds, CW, meaning both are present.
But the managers can't see those directly. What do they observe?
Just two things. Present, ZP, meaning they saw at least one adult weed, or absent ZA, meaning they didn't see any during the survey.
Got it. And what actions, A, could the managers take in the model?
They looked at three main options, each with different costs and effectiveness. First, the big one, soil fumigation.
Using methyl bromide. That stuff's pretty potent.
Extremely. Modeled as about 79.6% effective at killing the seed bank. Very efficient. But yes, it's incredibly expensive, around $18,000 for an average paddock, and it's highly toxic. So in the model, it's only ever considered if the weed is actually observed.
Makes sense. What's the next option?
Host denial. This is more about managing the environment. You plant crops that the broom rape can't parasitize. This gradually depletes the seed bank because seeds germinate but can't find a host.
So less aggressive, cheaper, better for the environment.
Right. Among less expensive, less damaging ecologically, but also less efficient. They modeled it as causing about a 50% reduction in the germination rate each year.
Okay. And the last action?
Do nothing. Basically, minimal cost, minimal effort. Maybe manage the land as pasture. You're essentially just letting nature take its course and hoping the infestation declines on its own.
Right. So fumigate, deny the host, or do nothing. Okay. They build this POMDP model with the states, observations, actions, costs. What did it tell them? Did it just confirm common sense, or were there surprises?
Oh, there were definitely key insights. The big one was that the best strategy isn't universal. It really depends on two main things: the reward-cost ratio of the site and the detection rate, how likely you are to actually see the weed if it's there.
Let's take the reward-cost ratio first. That's like,
Yeah.
how important is this specific paddock?
Exactly. Think about high-reward sites. Maybe it's an isothet outbreak far from the main infested area, or a farm right on the edge of a quarantine zone. Clearing that site has a big payoff for the overall goal.
So what does the model say for those high-value sites?
If the weed is detected, CP, the model says go hard. Use the most effective, albeit most expensive, action. Soil fumigation. That matches intuition.
Okay. But what happens next year? If you survey and don't see anything, ZA.
Now, this is interesting. If your detection probability, D, is high, say, you're pretty confident you'd see it if it were there, maybe D 0.7, the optimal action after fumigation and non-detection, is actually do nothing.
Hold on. You spend $18,000 fumigating, and then the best thing is to do nothing. Why not keep treating it just in case?
Because the POMDP weighs the costs and benefits based on your belief.
Right.
If detection is high, a non-detection strongly increases your belief that the site is now clean. The model calculates that the ongoing cost of, say, host denial outweighs the now low perceived risk of seeds remaining undetected, so you just monitor.
Okay. That requires trusting the model's calculation of risk. What about low reward sites? Paddocks deep inside the main infestation.
Right. Sites where clearing this one patch doesn't really change the big picture immediately. Here, the model flips. The value of clearing the specific site is lower, so the optimal strategy prioritizes cost effectiveness.
So not fumigation.
No. The optimal action, even if you detect the weed, becomes host denial. It's cheaper, less efficient, but it makes more sense economically for that particular site, given its lower strategic value. Why spend the big bucks fumigating if it won't shift the needle much overall?
Resource allocation. Makes sense. Okay, it's location dependency. What about the detection rate itself? You said that was the other key factor.
Yes, and this is where the POMDP really shines compared to simpler models. Imperfect detection changes what you should do after you don't see the weed.
How so?
Well, as we said, if detection is high, like 0.5 to 0.7, the strategy is fumigate when seen, then do nothing when not seen in high-reward sites. That kind of aligns with some current thinking.
But what if detection is low? Say only 0.1 to 0.3 probability of spying it.
This is the crucial finding. The optimal strategy changes after a non-detection. You still fumigate if you actually see it. But in the following years, when you survey and find nothing...
You don't switch to do nothing.
No. The model essentially says, look, detection is poor. Just because you didn't see it doesn't mean it's gone. There's a high chance you just missed it. So the optimal action becomes host denial.
Ah, so it acts as a buffer, a sort of precautionary measure.
Exactly. It's an intermediate step. It's less costly than fumigation, but it actively works to reduce that hidden seed bank, hedging against the high uncertainty caused by the low detection rate.
So if you ignored imperfect detection, like with an old NDP model, you'd see absent and think, great, it's gone, do nothing.
Right. And you'd potentially waste all the effort and expense of that initial fumigation because the seed bank could still be there, quietly persisting. The POMDP avoids that by recommending the protective host denial action when uncertainty is high. That's its real power.
Okay, that's a really clear advantage.
Yeah.
What about other factors? Do they look at things like reinfestation from nearby areas?
Yeah,
Colonization?
they did. They modeled the impact of a colonization rate.
And what happened? Did the best actions change if seeds kept blowing in?
Interestingly, no. The optimal actions themselves, like fumigate high reward sites if seen, use host denial if not seen but detection is low, those stayed pretty stable even as the colonization rate increased, up to about 0.15 in their tests.
But surely something changed.
Oh yes, the probability of actually achieving eradication plummeted. With zero colonization, C0, the model showed you could get the probability of eradication close to 1.0, near certainty, if you followed the optimal strategy.
Okay.
But crank up the colonization rate to just 0.15, and the best possible probability of eradication you could achieve, even doing everything optimally within the paddock, dropped to only 0.62.
Wow, so less than a 2/3 chance, even doing everything right inside the site.
Exactly. The implication is huge. If your goal is true eradication, not just control, then stopping spread between sites, limiting that colonization is absolutely critical. Paddock-level management alone can't win if it keeps getting reinfested.
That makes sense.
Hmm.
Were there any limitations acknowledged in the paper, things the model didn't capture?
Sure. They noted it was robust in sensitivity analyses, like varying the assumed effectiveness of host denial didn't change the core results much. But a key limitation is that the POMDP they presented isn't spatially explicit,
Right.
meaning it treats each paddock in isolation. Realistically, the best action for this paddock probably depends on whether its neighbors are infested or clean or being treated. Incorporating those spatial dynamics is a big area for future research.
Right, managing landscapes, not just patches. And did the findings challenge current practices? You mentioned the 12-year monitoring rule for broom rape.
It does offer a critique. That policy monitor for 12 years with no detections before declaring a site eradicated the POMDP suggests that's only really the optimal approach under very specific conditions, essentially zero colonization and very high detection probability.
Which might not be common in reality.
Probably not. In many real-world scenarios, sticking rigidly to that rule might mean you're doing nothing during years 3, 4, 5 after a non-detection, when the POMDP, accounting for imperfect detection, would actually recommend implementing host denial as a precaution. So potentially suboptimal management during those crucial years.
So summing up, the POMDP isn't just an academic exercise, it's a potentially powerful tool for managers.
Absolutely. It's a way to systematically combine all the messy parts, the costs, the benefits, the weeds biology, and crucially, that uncertainty about whether you've actually found it to get tailored recommendations for specific sites. It helps make decisions that are really hard to arrive at just through intuition.
Okay, so we've seen how this model helps figure out the best actions under uncertainty and how things like colonization drastically affect the chance of success, ranging from almost certain down to maybe 60-odd%. That leaves us with a final thought for you, the listener. Given all this, when should a manager actually pull the plug? When do you officially declare an invasive species eradicated from a site and stop spending money on monitoring?
That's the million-dollar question, isn't it? And the POMDP framework helps clarify the trade-off. Declaring eradication saves the ongoing cost of monitoring and management. But if you declare too soon, and the species is actually still lurking undetected,
It could escape, spread, cause massive damage, maybe reinfest areas you thought were clean.
exactly. So the decision involves weighing that cost of continued vigilance against the potentially enormous consequences of getting it wrong. You need to think about the true cost of escape for that specific species in that specific location and decide what level of risk, what probability of it still being there you're ultimately willing to accept before you walk away.